Next thing that we want to look at in chapter 6 is something called the specific heat capacity. Now, the specific heat capacity of any substance is defined as the quantity of heat required to change the temperature of a unit mass of the substance by 1 degree Celsius. Now, what does that mean, a unit mass? Well, a unit might be a gram, it might be a kilogram, it just depends on what value for specific heat capacity you're talking about. But here's the idea. I have a block and I put it over a fire. So the fire is adding heat to the block and the temperature is increasing. And so it goes up. So let's say this is a unit mass. We can call it, say, a kilogram, for example. So I've got a 1 kilogram block of lead or whatever the block is made out of. And I've got this fire that is warming it up. And so the fire is transferring heat. Heat is flowing into the metal. And what's going to happen is the temperature is going to increase. And so the question is, how much heat energy does it take to increase this kilograms worth of lead by 1 degree Celsius? That's the temperature change we want, and that's called the specific heat capacity. Now, there's a figure over here of a guy eating an apple pie, and before you read the caption, let me just talk about that for a second, because this is kind of a universal experience, especially if you like pie. What happens is, so you pull the pie out of the oven and you don't want to wait for it to cool down because you want to eat your pie. It's delicious. And so you cut yourself a slice and you kind of touch the crust of the pie and you see it's nice and warm, but it's not like burning hot. And so you grab your fork and you take a bite of pie, and when you put it in your mouth, you burn your tongue and you burn the roof of your mouth. Why is that? It's because the apple pie filling has a different specific heat capacity than the crust. What does the specific heat capacity tell you? It tells you how much heat does it take to raise the temperature of something by a certain temperature. So let's say you have placed your apple pie in a 400 degree oven and you've let it become 400 degrees. Now, the apple pie filling has a much higher specific heat capacity than the apple pie crust. That means it takes a lot more heat energy to raise it to the temperature of 400 degrees than it does the crust. And so this guy has absorbed a lot more heat energy in order to come to its temperature. Now you take it out of the oven and you let it cool down. The crust is, initially they're both at the same temperature, but the crust is going to cool off much faster because its specific heat capacity is much lower. It doesn't have to give off a lot of heat in order to cool down. But because the filling has absorbed so much heat to get to that high temperature, it has to give off a lot of heat in order to cool down, and that takes longer. So that's why you can burn your mouth on the filling when the crust is perfectly edible. Now, this is the equation that we use for determining the quantity of heat necessary to raise the temperature or lower the temperature of something. And so the equation says that Q, and that stands for the quantity of heat. Some books call it just H for heat, but Q is traditional, so Q stands for quantity of heat. It's equal to the mass times something called the specific heat capacity. That's what we've been talking about. That little c stands for specific heat, times delta T. Now remember, delta means change in, and in this case, T doesn't stand for time, it stands for temperature. And so this is the mass times the specific heat capacity times the change in temperature. That's what Q is, the quantity of heat. So I've written out what all of these are. The Q stands for the quantity of heat. Now, what does that mean, quantity of heat? It's the quantity of heat transferred from one body to another body. That could be the apple pie to your mouth. It could be the oven to the apple pie. There's a transfer of heat from one body to another body, and that's the Q. Now, if the Q is less than 0, in other words, it's negative, that means that heat is removed from the mass. It's cooling down. If Q is greater than 0, if it's positive, that means heat is added to the mass. It's heating up. let's look at an example. Now, in the example, it says 50 grams of water is at 20 degrees Celsius, and it's mixed with 50 grams of water at 40 degrees Celsius. What is the final temperature of this mixture? So what do you think is going to happen? I've got this cool water at 20 degrees Celsius, and I pour it into a cup that's got warm water at 40 degrees Celsius. Well, the warm water is going to cool down a little bit, and the cool water is going to warm up a little bit. And we know that by conservation of energy and the first law, the heat gained by the cooler water has to equal the heat lost by the warmer water. And because the two masses are the same, the final temperature is going to be right smack dab in the middle. So we'll have 100 total grams, 50 of each, added together at 30 degrees Celsius. And that is the temperature right in the middle. Now, if the temperature of the room is not 30 degrees, eventually that water will warm up or cool down to the temperature of the room. But it's the same process repeated, but in this case we're looking at just what happens immediately after we mix the two temperatures. When they come to equilibrium, it's going to be 30 degrees Celsius. Let's look at another example. Consider mixing 100 grams this time of 25 degrees Celsius water with 75 grams of 40 degree Celsius water. Now they're not the same mass, so what's going to happen? The question is still, what's the final temperature of the mixture? And the rule is that the heat lost by the warmer water equals the heat gained by the cooler water. So we can use our formula for the quantity of heat in each case. For the warmer water, it's going to be M1C delta T1, and for M2 for Q2, it's going to be M2C delta T2. Now it's the same substance, so the C's are going to be the same, the specific heat for water. And that's something you'll either be given in a problem or you can look up on a table or with Google. But basically, you're always going to know what C is, and you're just going to plug the number in. Now, in the problem, we're looking for the final temperature. Now, we don't know what the final temperature is, but we could probably guess that it's going to be somewhere bigger than 25 degrees and somewhere lower than 40 degrees. It's going to come to equilibrium somewhere in the middle. So we've expressed this here that the T final is going to be bigger than 25 degrees and smaller than 40 degrees. And so the change in temperature for mass 1, and we'll call that delta T1, is going to be the final temperature minus 25 degrees. Now here's where it gets tricky. For the change in temperature of mass 2, it's going to be 40 degrees Celsius minus the final temperature. That's how much it's going to change. And so that gives you your delta T2, and that gives you your delta T1. So now we can use our equation. M1C1 delta T1 is equal to M2C2 delta T2. Now, in the last slide, we showed that delta T1 is T final minus 25 degrees, and delta T2 is 40 degrees minus T final. And so we can plug in for M1 and M2. That's going to be 100 grams and 75 grams. That was given in the problem for those two masses. And then the specific heat of water is 1 calorie per gram degree Celsius change. So 1 calorie per gram degree Celsius. And when you multiply everything out, you get 100 times TF minus 2,500. Now I'm being a little sloppy with the units here. The units all have to work out, but you can see this. The units are really messy, and so I'm just going to kind of wait until we get to the end. Because we know it's a temperature, the final units have to be something like degrees Celsius. And so I've got 100T minus 2,500 is equal to 3,000 minus 75T. And that comes from just multiplying everything out and adding and subtracting everything together. And so if you do the algebra, you're going to move this guy over here, and you'll get 175 times TF. You'll move this guy over there, you'll get 3,000 plus 2,500. You end up with 175 TF equals 5,500. If you then divide both sides by 175, you get the final temperature, TF, is 34.1 degrees Celsius, so about 34 degrees. And that is the answer. The next thing we want to look at is thermal expansion. Now, when you have a block of a substance and you add heat to it, what happens? The atoms and molecules, they start vibrating back and forth more rapidly. And so the temperature increases. But they also vibrate in back and forth with bigger swings. They go faster back and forth, and they also go over larger swings to and fro, back and forth. And so what's happening as the atoms vibrate and they take bigger swings, the material basically expands. And so these are the two things that happen when you heat up a block of something. One, you increase its temperature by making the molecules vibrate back and forth faster, but you also tend to make it expand, and so it will grow. And so that is called thermal expansion. And that's just the expansion that occurs when you add thermal energy to something. Here we see some images that give you the idea. So on the leftmost picture, you can see that thermal expansion has wrecked these train tracks. And so what happens is the train tracks weren't built with any give in them, and so as they expanded, they buckled. And so that, just basically destroyed. You couldn't have a train run on these tracks. The train would derail and crash. So engineers have to account for thermal expansion of things to prevent this kind of catastrophe. Now, here's an example of something that can prevent that sort of thing from happening. We have in Figure 6.15. This is basically a segment of a bridge, and you can see that the bridge is resting on this guy, but it's not anchored to it. It's not screwed in. And so as this beam expands, it's not held in place, so it's not going to buckle. Now, the other end of the bridge is anchored, but this one is not. It rides on these rockers, and it allows for this expansion. Another example of this kind of engineering can be seen in the figure on the right. And so we have a gap in a roadway of a bridge, and you can see that they're like these teeth that are interlaced here, and they're not meshed completely together. So as the bridge expands or contracts, these teeth can separate or get closer together, but there's enough room for the expansion of the bridge. And if this seam weren't here, the bridge, as it expanded, it would press and it might buckle here, and then a car driving over it could fall down and crash. Now, most things behave in a similar way. Water is an exception. Water behaves in a weird way. When it solidifies and forms into a solid, it actually ends up taking up more volume than the liquid. And this is very unusual. But this is why ice tends to float. If you have a glass of water with ice in it, the ice is going to float because the ice is less dense. Why is it less dense? Because in the process of freezing, it's expanded. And the reason for that is, so here we have a picture showing water in the liquid state, and it's very dense. All the molecules of water, H2O, are vibrating back and forth, but they're all packed together. But as you cool it down, the bonds connect to make it a solid instead of a liquid, and the bonds connect in a way such there's a lot of space in between the bonds. And you can see the sort of geometry that occurs here, and that creates a lot of empty space, so the ice crystals are actually expanded. And so ice crystals in nearly frozen water are taking up a lot of space compared to the water itself. So the solid part takes up more space than the liquid part. So this is showing how the volume of water and ice behave with temperature. Now the blue curve here, is indicating the normal expansion of water with increasing temperature. So we'll have water increase the temperature, the atoms and molecules are vibrating back and forth, and they're swinging with bigger swings, so they want to get wider. They want to expand like a normal substance. But the green curve shows the contraction of ice crystals in water as they melt with increasing temperature. And so the combination of these two together gives the red curve. And this shows how the volume of water behaves with temperature. And so you can see that at 0 degrees I've got ice, and as I melt the ice and convert it into water, the density actually decreases. And at 4 degrees Celsius, that's the smallest density of water. That's the lowest density of water that you'll find. And then as you heat it up higher temperatures, the normal of expansion of a substance with increasing temperature takes over and the water begins to expand again. But right near the freezing point, it behaves in a really weird way. It doesn't just go straight up, it dips down before going up. And the maximum density of water, where the volume is the least, is at 4 degrees Celsius. So when you have ice at 0 degrees and you start to heat it up, it starts to melt. And basically, the liquid part of the water still has these crystals of ice in it taking up space. And so liquid water below 4 degrees Celsius is generally bloated with ice crystals. Upon warming, these crystals collapse, and that reduces the volume in the liquid water, and so the volume goes down. But after you get about 4 degrees Celsius and you continue to increase the temperature, that normal expansion kicks in again. And so that's why we see this weird behavior with water. Now here's the fun thing about that. What that means is that rivers and lakes and big bodies of water are always going to freeze from the top down. So let's say it's really, really cold, like 10 degrees below 0 Celsius, and we know that ice freezes at 0 Celsius. And so what's going to happen to the water? Well, in a normal liquid, the solid state would be more dense than the liquid state. And so as it solidified, it would sort of solidify. The solid parts would sink down and it would, freeze from the bottom up. And the whole thing, the whole shebang would freeze. But with water, it's a little bit different. Because what happens as the water starts to get colder and colder, when it gets to 4 degrees, that's when it is most dense. And so you're going to have water that is, maybe 6 degrees here, it's cooling down. When it gets to 4 degrees, it sinks because it's most dense at 4 degrees, and that's going to push warmer water up top. And so the whole thing has to cool to 4 degrees before the layers at the top can be made even colder than 4 degrees. And so add to that water has a very, very high specific heat capacity. Basically, this is what enables fish to live, because the ice freezes at the top, leaving a big body of water underneath for the fish to swim around in, which is kind of cool.